for people who want to find live presentation to participate, and also conferences. Actually, I was sort of saving it to the end, but if we already mentioned it, here is a Java conference that starts tomorrow, or is one day tomorrow. And it's a free Java conference. Normally it would not be free, I believe. And now anybody can access it from anywhere. And this is not an AI conference necessarily, but it's a Java with a lot of pretty good people presenting. And then there is DevNexus. If you see my shirt, you can't really see the whole thing, but I'm wearing a shirt from DevNexus. This will take place in February in Atlanta, like it does every year, but the next one in February will actually be virtual as well, and probably free as well. So check out the DevNexus, which is at least it claims to be the biggest Java conference in the United States, at least one of the biggest ones. So let's go into the presentation. Can you see that my screen? Do you see the PowerPoint?
Yes, we do.
Okay, so generally speaking, just before I start, what I'm going to talk are two things. An introduction to machine learning, which is a basic introduction. The idea is that if you don't know anything about it, it will get you somewhere to some understanding about machine learning, but just the beginning of it. There is a lot more. And then a lot of the presentation is about Java tools to do that, because we know the status is that Python is pretty much the prevailing language, but you can basically do anything you can think of. There is all kind of Python libraries that will do that. And people who are graduating, people who go to school and study AI or machine learning or take classes, they will almost exclusively learn it with Python. However, we have a situation where the enterprise software is mostly written in Java, a lot of it. Java is the prevailing language when it comes to all kind of existing applications, and a lot of companies are Java shops. And what happens is you have situations where a company will have, which is a Java shop now, wants to introduce all kind of machine learning and AI capabilities, which is becoming a commodity. It comes everywhere. You can combine it almost to any product. And then they face a problem and they say, so what now? We're going to have Python developers side by side with the Java? Are we going to change our DevOps to be able to support both and somehow combine more? And they would prefer normally to do everything with Java. So I've been consulting to one company that has done that. And so far we were able to keep it Java, even if the people start the research and development are Python people. Eventually we always have a way to turn it into a Java product that will be deployed and actually written in Java code. So these are the two things I want to cover here as much as I can. So about me, I've been into AI and machine learning for many years since I graduated grad school, which was in the 90s. But I've been working as a Java developer. Along the way, also genetic algorithms is one specialty of mine, which is somehow related to AI, and also it can be tied into machine learning, and I'll mention it a little bit later. So I wrote that book. The book is in Python because these are the people who mostly would read that book at this point. But anything you can do with it in Python, you can do it in Java as well. And that might be a separate presentation. I ran with Vivian, who is with us here, but did not present itself yet. We run the Enterprise AI Virtual User Group, so you are welcome to join us there. Every month we have some guest that talks about some related, it's not Java, it's not language specific usually, but it's an interesting user group. And the time of the user group is about the time that we are now. So it's probably convenient for you in South Africa to join this group as well, to participate. So check it out. I also run the Java, the the Jacksonville Java user group, which is Jacksonville is in Florida, not a very famous city, but it's up there in the Northeast, and it's called also First Coast, because if you enter Florida, coming down from New York, for example, you will enter probably pretty much via Jacksonville, and it's the first Florida coast you will come to. And I have this blog that you can see down there that I started a while ago, and I need to go back to it and publish some more posts, but you can use it to get started with machine learning in Java and also with deep learning in Java, some stuff that I will cover today with a little bit in a nutshell. And I'm an author of this book that we will also get back to at some point. So let's just start with talking about machine learning. If machine learning is new to you, and like we said, we have Zoran here. Zoran that is here, I guess, actually is one of the prominent Java guys nowadays that are trying to make the Java a first-class language when it comes to machine learning, and to basically give a fight to Python. And we will see some of his work at some point. Maybe he will even want to say some things. But I think Zoran is the one who ran some kind of a survey among Java developers, asking them what is your biggest difficulty with machine learning. And actually the biggest difficulty is that they didn't really know what is machine learning and how to get started with it. So here is a little bit of what is machine learning and what are basic concepts. And the idea is that in machine learning is that somehow we write a program that looks at data and learns somehow to do certain things just based on the data and not by specifically putting in if then all kind of logic that is specific to the problem. There is a program there, there is some logic to the program, but the program basically looks at data and changes the behavior of it according to the data. So we'll try to explain how this is done. So here we have three general kinds of machine learning. There are maybe some more niche ones, but generally speaking, it's supervised, unsupervised, and reinforcement learning. The supervised one, I believe, is probably is still the most commonplace, but also is the most intuitive to understand, I think. So let's talk about that today. So in supervised learning, we are trying to create something that we call a model. So our program really is the model. And what we want is to put inputs into the program. A model basically gets inputs and generate outputs based on those inputs. And also it has all kinds of internal parameters that when we go through this data, there is some algorithm that goes and tunes those parameters, changes them according to the data. And how it tunes the parameters is because we have a set of data where we know what the output should be for that data. So we enter the input and we tell the model, this was supposed to be the output. So the model looks at the output that we tell it, and it looks at the output that it generated by random perhaps at first, while the parameter values are sort of random at first. And then it says, okay, let me change a little bit the parameters. Let's see how this goes. And then we put more data into it, or the same data over and over again, and it keeps changing internally those parameters until at some point the data, if the model is good enough, and we gave it enough examples, it will eventually be able to reproduce the output that we wanted for the inputs, for the matching inputs. And then, ideally, when we start putting new inputs that we did not show the model before, then it will produce correct outputs, or mostly correct outputs, and we have ways to measure that. So this is very abstract. Let's just make it a little bit more, perhaps, concrete. So let's talk about two cases. One of them is a classification, what these models do. So in classification, what we want the outputs is the outputs are called labeled, and we basically want the inputs are called features. And we say for these features, we want one of these labels to be true and the rest of them not. So we want basically to figure out what category this input belongs to. So for example, the most famous data set that is used for learning, for looking at, for maybe trying out examples, is the iris flower classification. So we have three kinds of iris flowers that were participating in this research that somebody did many years ago. So they have this data set that says these are the length and the widths of the two kinds of leaves on the flower. And based on that, tell me which of the three kinds it is. So generally you will have an input here of four numbers, and we want one of these outputs to be high and the other two to be low. So like 0, one of them will be 1 and the other one will be, let's say, 0. So every time there will be 4 numbers here, and the outputs here will have to be ideally 0, 1, 1, or 0, 1, 0, etc. One of them. So they may not be exactly that, but we want them to be close to that. But this is at least what we tell the model that we want. So then the model goes and tries to change the internal parameters somehow until it gets to the point where it gets good results and can imitate the zeros and ones that we told it based on the inputs. And then we say that it finished learning. Here is a more interesting example, perhaps, where the inputs are actually pixels. So this is a handwritten digit classification. And what we have here, the inputs are grayscale images. There are 28 by 28 pixels, I think. That gives us 784 inputs. So each pixel is being fed directly into the model. And each of them can be between 0 to 15, the gray level. And then what we want in the output, if it was a 3, we want the output that says 3, we want that to go high, and all the rest of them to go low. And this is what we are going to try to teach the model. And the other kind of, okay, so here are some other examples. They can apply to a lot of things, like do we approve the loan? Do we give a credit card to the person based on all kind of inputs? Is the person sick or not? Or what kind of sickness it is? Is it me or somebody else? Is it one of the people that we know or not? A friend or foe, etc. Is this mail spam or an okay mail, and etc. etc. Many uses for this. The other kind of supervised learning that we want to talk about is called regression. So here again, we enter the features, but the output is just one, but it's a continuous output. It will be just a value. For example, it will be the market value of a house. So the inputs will be all kind of information about the house, like we see here in the example, but it could be, usually it will be a lot more than just these 3 things. And then we want to estimate the house, the market value. So how do we do this? Again, we have all kind of examples. We say, okay, this house has all this information, and we know that the price was that. And this house, the price was that. We run it through the model. The model goes and tunes internally the parameters, and eventually starts to get the results correctly. And then we can show new prices. And these are other things we can do. If you go about stock prices, we can try to learn what were all kind of situations and what the stock price was. We can maybe forecast energy consumption based on all kind of data about temperature and previous readings. I saw somebody who was trying to figure out how long it will take when you upload the document for processing in some application, how long it will take based on time of day and previous cases. You can maybe predict when something needs maintenance, and many more other uses for it. So those, let's just go back. So those mysterious models that we spoke about, they are basically software creatures, let's call them, that were invented over time, and there are all kind of them, and they all have in common the fact that they are learning in the sense that they are changing their internal parameters while doing this learning process, while we show them input and output. So we can't go too much into them, but these are some of the main ones. I think decision trees are probably the easiest to imagine. Decision trees make their decisions based on the inputs. They say, if this input is more than this and this, they build the tree internally. So the internal parameters that we are going to tweak during the learning are those parameters of the trees where to do the branching. And the algorithm of the decision tree will do it internally. And there are many kinds of them. Random forests are sort of the next level, where you have a lot of trees. But there are other boosting models, etc., that use a bunch of trees at the same time. Support vector machines is another kind that just is mathematically capable of doing all kinds of manipulations. And the one that I will speak more about soon is artificial neural networks that leads us also to deep learning. So let's keep this in mind. First, let's talk more about this machine learning, that all these algorithms that we have. So we know that in Python we have a lot of tools, and scikit-learn is probably one of the most known of them to run all kind of machine learning algorithms. Java also has a lot of tools that were created over the years, and these are a lot of them. These are some of them that I mentioned here. Some of them are quite old, like Weka, and some of them, like Smile, are pretty good, but they are not. Some enterprises shy away from them because of the license. What I'm very excited about is the last one here that's called TreeViewer from Oracle. This is an open source project from Oracle that just right now, basically, these days is being released and exposed, and you can already use it. And I think that if you are starting with this may be your first place to go to trying to do machine learning. And what TreeViewer can do, and this is the web page right here, and basically trying to give a fight to scikit-learn. So you can use this dependency, or you can break it down to smaller dependencies if you only use part of it. But these are things that it advertises itself. Instead of, you can read it yourself, but I have a summary of it here. It's strongly typed. It's very Java-like. If you like Java, you will like working with that. Unlike Python, where types don't really exist, and it's trying to also build on that and provide what we call provenance, where it basically, if you train a model, if you save a model, bring up a model, the model will remember everything that was done. It will remember what kind of data came in, what were the parameters of learning, etc., and it will basically prevent you from trying to put different kind of data or making other mistakes, or also just give you the history and the information about what happened prior to the model being used. It can, TreeViewer can also work with other libraries, so you can take things that you did in Python and bring it in. I will not talk too much about it, and the Apache 2 license is important because it means that you can pretty much use it to your liking in an enterprise applications. So let's do a quick demo with that. It's just something that I did recently, playing with it. That's not the correct one. Can you see this? Can you see my eclipse here?
Yes.
Yes.
Okay, so this is very much like, I'm going to put my glasses on because this is sort of small now. This is pretty much following one of their tutorials. There are a few tutorials there in TreeViewer, and they're written as notebooks, which is another thing that I won't go too much into it, but notebooks are, you can basically something that you can run online interactively. But here it is just done as a class with the main function that just called this method go. So what you can do, because here we do classification, we are talking, it's called the basic data structure here is called a label. Just let's look at the data. I mentioned that before. So this is the iris data. What you see here, this is what the data set looks like. This is a small data set. So it has 4 numbers here. It's a comma delimited. So these are the 4 inputs, and then this is the output. The output is a class that's called this or this or that. So you see the first, it's divided. So you have 50 examples of each. But this is really what a data set would look like. Normally a lot bigger than this, but you would have numbers or sometimes not numbers. Some of the inputs can be other things than numbers. But definitely the output here, this is why the output is called label, because it just tells us what it is. And it will be represented by zeros and ones like we saw. So if we have 3 different labels here, 3 different possible labels, then we will have 3 outputs. And we want one of them to be 1 and one of them to, the other to be 0. So we basically, what we do here is very similar to what we do with any language that we want to upload a data set and run learning on it. So we just follow the same idea, but in the Java, in the TreeViewer way. So here we have a label factory, and then we have a CVS loader that is just basically we tell it that it's a label, it's a classification, multi-class classification, what we want to do. That's why it's a label factory. Also, we add headers to this file because it doesn't have them, so we can refer to them by name. So these are actually the meanings of the 4 numbers, and this is the meaning of the output is what species it is. Well, you can call it whatever we want, but this is what we chose to call it, which is the official names. And then we create a data source by loading that file from the path, and we tell it these are the headers, and species is the output. Here we actually tell it which one is the output. And then we do something that we do very often. We have a data set, we split it to training set and test set, because we want to train the classifier in this case, or the model. We want to train it, but we want to test it on the data that it didn't see before. So we decide here to split it to 70% of the data will be used for the training, for the learning part, where it is going to know the answer. And then the other 30 will be used for the evaluation of how well it is generalizing, how well it applies that knowledge to new examples that it hasn't seen before. And we use some random here because we wanted to shuffle the examples. Otherwise, you saw that the examples are 50, 50, 50, separate ones. We want them to be shuffled around. So I can just start running it in a debug mode. And it will stop here, and it will print out what the data looks like. So here you can have some information about the data. You can, once you created this training data set and test data set, you can get a feature map, and you can say the size and other things. So it's just printed this. This is my output for these two statements here. So it knows that there are 4 features, 3 classes, and that's true for both of the classes. And the way it was divided is 105 and 45. So now let's do the learning. The way it's done in Trivio, you create a trainer. And where is the trainer? Oh, I'm sorry. The trainer is here. I sort of skipped that. I should have maybe put a trainer. Let's do it now. Let's bring it down here. It will look better. No, I'm sorry, that is not correct. I need the trainer actually for the split. So what am I missing here? I'm missing here something. I'm sorry, this always happens when I do live coding, even though it was only for here. This is what I didn't notice. So we create a new trainer, and the trainer is basically, this is the model that we're going to use. So there are different models. Logistic regression is actually one of the simplest one. And it's confusing because it has the name regression in it, but it's actually not a regression. What we do here, it's classification. So it's a classification model that's called regression, logistic regression. But what he tries to do, he tries to create some curve that separates the two groups from each other. And then you have the more, if we go back here, so this is here, and then you have all kinds of decision trees, etc. that we can use as well here. We will have to choose a different model here. And models that are more complicated will have a lot of parameters that we can set. These are parameters that are not part of the learning. They're called hyperparameters. We set them to begin with, and it will use them throughout the learning itself, like the learning rate, or the number of branches in the tree, or the number of little tree in the forest, etc. So now that we have the trainer and we have the data, we can just basically train it on the data set. And once we do it, we have an evaluator that will show us all kind of information about the learning. The evaluator is part of a Trivio, and it will basically spit out all kind of pre-programmed information about the learning. So if we keep doing it, here are the training results. It's a lot of information, and maybe not the best, maybe somewhat confusing, but basically there are all kinds of ways to measure how we learned. The most basic one will be the accuracy. So if we look at that accuracy, we see that basically, and that means that in 98% of the cases, we got it correctly. But we can also look at other measurements that will tell us how many false negatives, true positives, etc. Sometimes it's more important to minimize one of these measures rather than just accuracy. And so these was the results for the training. So basically, these are the examples that we knew the answers, and we were feeding them into the model, and the model was trying to basically understand them. And usually the results, if the model was good enough, the results will be good, but the real test is the test set where the model has not seen those examples before, and now it's trying to generalize on those examples. So now we do exactly the same thing, but we give it the test data set and not the trained data set. So if I run this, we see the same results for that data set. So the results are not as good, but in this case are still reasonably good. They are 91% in the accuracy. And you can see that there are more errors here. Then the next thing that we do here that is sort of a special for Trivio, we will not do that if we had a Python model, if we had a Python program, is use the provenance, which will give us the information about this model and how it was created. So we just print it out. And maybe I can make this bigger. So this is the provenance here. So it gives us, so this is the provenance of the model. And it tells us that we had a splitter coming into it. The source was CVS. It basically tells us where everything came from. Which is what you see here, I'm sorry. And where are we in the running? Okay. And the last thing is the training provenance that gives us information about what happened with this data when we trained. So this is some more information that tells us how many epochs were and what was the optimizer used internally within that. This is part of the learning algorithm that's used inside the logarithmic regression. So this information can be used here. We just printed it out. So I hope you forgive the choppiness of my presentation here because the first time I actually did that because it's brand new. And with this promise of Trivio, let's move to neural networks. So let me talk about neural networks, which is related to, it is a kind of machine learning. So I'm going back there. So artificial neural network is a lot of models, and some of the most interesting models that were created eventually after things started evolving, but also 20-something years ago when I was in grad school, we did stuff with neural networks. They just weren't as elaborate as they are today. And they were inspired by biological neural networks like the ones we have in the brain. So we start with a very small unit that's called a neuron. Our brain is made of many, many of those, but each one of them is rather simple. What you see is it has inputs where on the left side, and there is an output that gets connected to other inputs like that. And what we have here is some kind of decision making that when it decides that we actually saw something interesting, then it fires a pulse and it triggers all the other cells that it's connected to. And it by itself makes the decision by all the inputs that are coming in. Let's see sort of a mathematical representation of it. What we have here are inputs that have weights. So the inputs are not do not have the same importance. The bigger the weight is, the more importance it is. And what it does, it will summarize all these inputs with their weights, weighted sum. Then there is another number that's called a threshold or bias. And altogether, basically what it means, if the sum of inputs, the weighted inputs is more than the threshold, it will fire in the real neural network here. It will just go through this non-linearity. So the output will actually be continuous, but to actually get to the high values or to the very low values, you'll have to, the weighted sum will have to be very different from the threshold or the bias. The bias will try to bring it to the zero where it doesn't do anything, but a certain amount of input combined with the weights will try to push us towards one of those sides where it's significant. So why is it important? What can we do with that? What the real power of that is when you have a lot of them connected to each other, and we connect them in all kinds of interesting ways. The most straightforward way to do that is called a feed-forward network or a multi-layer perceptron. I have my dog here running over stuff. And what we do in this case is we create layers and layers of those very simple perceptrons, and each one of them is connected to all the ones that were in the previous layer. So we get here a huge amount of connections, and that gives us a lot of power because each of these little neurons actually has some nonlinearity in it, the nonlinearity being this. So it makes a linear combination of the inputs, but then it goes through some nonlinearity, and that gives us a lot of power to actually create a very, very complex relationship between the outputs and the inputs. Now the inputs here don't do anything but convey the value in, but all the other layers coming after that, they have the weights and they have those nonlinearities. And the layers that are in the middle are called hidden layers. They're not in the input or the output, they're somewhere in between, but they provide us the true power of this network. So when I was in school, we would have either one or two of those hidden layers. And it became too complicated to try to do the learning when it's more than that, because you would have a lot of weights and you would have to take basically the way it works here. It takes the error, when we know what the error is, it takes the error, back propagates it and tries to correct all those weights. And if there is another layer, it will go back to the next layer and correct all the weights. So it can be quite complex, but in the many years that passed since then, we got to the situation where we can have many, many of those layers and have very powerful models, and it requires powerful computers and GPUs usually to handle this calculation. GPUs are the graphic processing units that actually are very good at doing operations like this. So they're used a lot to train the gigantic neural networks. So here we again see just a simple neural network, but if we wanted to use it for our classifier for that, the number 3 or whatever the pixels that are being input, then we could just have an input layer that will accommodate to 784 pixels, and then perhaps one layer, perhaps many. But at the end, it will have 10 outputs that one of them will go high and one of them will go low. And as we train it, we'll always tell you this is what the output should be. And the algorithm of this model, which is a backpropagation that I described before, will go and correct the weights and correct the weights. And we will keep doing it over and over again until the network will learn that. Now, also, what happened when using that, when it comes to processing of images, videos, and also sound waves and some other kinds of information, a new kind of neural network was developed that had a little bit more feature extraction built into it. And these are called convolutional neural networks. I will not go too deep into them, but the idea is that the first layers will basically concentrate on a group of cells at a time, and we'll try to extract very small features from them. So if we, for example, had a picture of a car with a lot of pixels, there will be different filters trying to extract features from it that will perhaps be different directions of edges. And then the next layer will try to combine those together and get higher level features. Oops. Eventually maybe leading to a wheel or a window or other features of the car. And eventually, as you go up the layers, you will get to a place where the whole concept of the car will be perceived. And all this is done not because we told it to do that, we just set what the structure of the network is, but it will do this feature extraction by itself, basically by training and training and training over and over the examples. But we have actually ways to see what it is that those cells are filtering for, what they're looking for, and it's quite fascinating. Well, these things are so powerful that it's actually scary. It's also scary to see sometimes what kind of computer power is needed to train them, but in many cases you can take those networks that were trained and just use them, or just add a little bit more specific information to your information and do something that's called transfer learning. And then, like if you have a network that somebody already trained to recognize faces of people, perhaps you can add the faces of the people in your organization to it and not try to train it from scratch. So there are many, many frameworks for deep learning. Most of them, as you may be able to tell, are Python or C++. Even the Python ones are actually based on C++ usually. But we do have a few Java networks, Java frameworks that can do that. Deep Learning for J maybe was the first, I would say maybe a commercial enterprise grade one in the last decade. And it's very capable, it does a lot of stuff. You can see here some of its features, some links, and also this is my tutorial that talks about it. The tutorial actually starts like today from the basics of machine learning, and it brings you up to a point where you do some programming with the AI for Java, with the deep learning for J, which I don't have time to actually show here. So this is maybe the most mature Java deep learning framework, and it's pretty useful. More recently, but also did a lot of progress, is the Deep Java library, which is made by Amazon. It's an open source project. And it's actually implemented within AWS. So it lends itself nicely to work on a Lambda. So they have some interesting examples of Lambdas doing that, running models. Actually, what this framework does, it encapsulates a lot of other frameworks that were trained that are not Java, that were maybe trained with C++, but it encapsulates them and it lets you choose existing models and use them and serve them as a Java, basically put them into a Java application. And also you can basically refer to them as they were Java, even though the internals were not. So you can they have something called a model zoo. You have a bunch of models doing all kinds of different things. And you can train them further. You can do a transfer learning that we mentioned, basically add some more capabilities that are more specific to your needs, and then use them. And again, it has the Apache 2 license, and they have an interesting demo site that is relatively new. Let me see if I remember to put it here. So this is the AI for Java. See if I can move this around here. So this is my website. You can go there, but you can just go to these tutorials on the right side. And this is the DJL demo. I'm trying to move this back. So for example, one of my favorite demos is the Doodle Draw. So the Doodle Draw basically is a JavaScript application running now on my browser, and I'm going to open where is it? This. Going to look at the network activity to see what it's sending to the backend. The backend, I believe, to be a Lambda on AWS, but why do I not see that? Here it is. Okay, so let's go to network here. Can you see that? I hope you can see something. But what happens, this doodle, what it will do is, I will doodle, it's JavaScript thing, but every time I pause, it will take that picture, send it back to the backend, to the Lambda, and the Lambda will run a very powerful neural network that tries to find what it is. It's trained to basically detect all kinds of shapes and objects, and it will return something that says, that's what I think it is, and it will actually give you a list. So I don't know, let's just do something like this. So I'll pause for a second. What's going on? I don't see the labels. Is this because it's hiding behind? But you can maybe, what you're going to see is the response. There's no response yet. I'm not sure. Why not? Oh, so now we're starting to see things. So what you see are the labels that are returned by by the network that's standing behind it. So right now it doesn't make a lot of sense, but you see here all kind of, there is a hockey puck, but these are very low probabilities. You see this is like 1% probability, 5% probability. 57% probability, it's a BlackBerry. But let's do this. Let's see if it thinks otherwise now. So now it says cookie or power outlet. You see, and you can see, oh, I need to go a little bit further here. So the cookie is 24%, power outlet 90%, and etc. And I can try to see if it now sees a face, perhaps. So now it says smiley face, or face, or Mona Lisa. So you can see the smiley face is 30%, etc. But that's because my drawing capability are not so great. Like if I started from a circle, it may have done a bracelet, circle, etc. And then if I do this, it may say frying pan. And if I do this, maybe, oh, I screwed up a little bit, but maybe it will second. But it's a sort of a cool way, a cool thing to work with and see what it might think. So today my drawing capability were subpar. So we come here to the next tool, which is called DeepNets. And DeepNets is the creation of Zoran, who is with us today. So let me tell you quickly what I know about it, and maybe Zoran can tell us a little bit more. So Zoran actually created a Java spec that's called the JSR 381 visual recognition, but it's really more generalized for machine learning. And this is one step in the direction of Java becoming more officially supporting machine learning and AI. And in his website, or this tool, which I believe is meant more to be as a teaching and learning training for developers tool, has all kind of interesting wizards and a lot of ways to get started in a very convenient and supportive way. But also the DJL itself that I mentioned before, I think has implementation of that spec. So the DeepNets is a reference implementation of the spec, and the DJL is already implementing it to some degree. But you can do a very, you have all kind of basically GUIs and ways to get started and create applications using GUIs and wizards. Zoran, I hope I did not misspoke about that framework. Can you tell us some more? Is Zoran still here? Okay, that's a shame. Maybe I should have started with it. But Zoran is accessible. I mean, even though he's a celebrity and he did all this stuff and he's a Java champion, we can actually access him and ask him more questions. But so this is a tool that's promising basically to bring Java more into into officially supporting AI. So I actually went even faster than I thought. So I came here to a subject that is a little bit more advanced. That's called AutoML. AutoML, the idea is that a lot of frameworks nowadays actually try to figure out the machine learning for you. Because as a developer, if you go and encounter a problem that you want to solve, we already saw that we have all kinds of models that we could use. We have all kinds of deep learning network types that you can use, or you can use combinations of them. And it's not obvious usually what is the best thing to use. There is also an aspect of the data. So what we saw here when we were looking at the iris data, it was already nicely cleaned. Let's look at it again. I'm again looking at the wrong place. Let's look at that. So usually this is like the last, this is where you want to get to teach the model, but in many cases you need to, before they decide what are the features that you want to have, what features are more important, perhaps what representation you will use in the features. What will you do? What would you do when features are missing, or for some of the examples? What would you replace the missing numbers with, and etc. etc. There are many decisions that you could make, and all kind of cleanup that you need to do, and that could prove complex. Let me go back to the presentation. So in many cases, you need a real expert and maybe some wizardry or guesswork to find out what is the best way to solve a particular problem. And to try to address it, quite a few frameworks are existing now to do AutoML. Basically, you will have to tell it what the problem is, what are the information that you have, what are the data features, etc. And it will try to find for you basically what is the best model, algorithm, parameters for the algorithms, etc. And this is an interesting subject of research that is ongoing, but you already have a lot of frameworks that do that. So if you use clouds like AWS, it will have something called AutoML. If you're familiar with the H2O, which is another framework I didn't mention here, but H2O is a very powerful framework that also is actually built on Java, but doesn't have a Java interface. But you can somehow use it with Java. I just didn't want to go into it now, but you could use it with Java, but it has a driverless, they call it driverless when they have an AutoML. And then you have Teapot and Ludwig, which I think are Python. And there are all kind of actually new things in this field all the time. And I've seen recently also in the deep learning. In deep learning, it's more complicated because you have so many, the networks are a lot more, you can decide like the number of layers, the number of nodes in a layer, how the layers are connected to each other. You have a lot of architectural parameters that you can set. And the training a network takes a long time. So if it's a big enough problem, so doing AutoML with neural networks, with deep learning can be very challenging, but there are now a lot of new advancements or new frameworks that are trying to tackle that. One of the ways to deal with it is with genetic algorithms. So some of the frameworks use genetic algorithms to some degree. And genetic algorithms is my pet peeve. That's one reason I'm bringing it up here. Genetic algorithms are an interesting way to solve problems by using the principles of Darwinian evolution, where the idea is that you have a generation of solutions, a lot of possible solutions that are at first random, but as you test them out and compare them to each other, you create a new generation that is built of combinations of the better solutions that you had in the previous generation. And as you progress from generation to generation, you get better and better solutions. And eventually you end up with, you normally end up with good solutions. So some of those frameworks will use genetic algorithms to find the best combination of what model, what parameters, what number of layers, etc. So that, oh, I'm already here, okay. So that was the subject of my book. I see that the next chapter, the next slide is about the book. So I wrote a book about it, which is genetic algorithms with Python. There are, however, genetic algorithm frameworks with Java. Let me just find one of them. I should have prepared it in advance. There is one that's called, I think, genetics.io, like this with a J. So this is a very new, relatively, it works with Java, I think 8 and above. And it uses all the latest streams and it has inherent concurrency, etc. So it's very powerful. But we can maybe talk about genetic algorithms some other time. What you could do if you're interested in it is go to this link or take a picture of this, and then you can get a free chapter of my book that talks about machine learning and how genetic algorithms, that's the first chapter in the book that talks about how genetic algorithms can help when it comes to machine learning. So in this, I think this chapter is how you can select the best features for a particular problem that are the most meaningful features for the problem, because sometimes you have a lot of data that is, a lot of it is not relevant or actually noisy, and disturbs the model. It also, if you do that, it will put you on the mailing list of AI for Java, and you will start getting the posts, unless you opt out of that. So basically, I think I went over everything I was going to, and maybe a little even faster than I planned, but it's not a bad timing. It's about an hour, I think. So let me know what questions you may have, or what I maybe could have done better or didn't cover today that you would like to hear more. I'll stop sharing and open to questions. And only now I can look at all your comments that I didn't see until now. Okay, so we had Manny here.
I have a question. Generally, what's a good way to pick a model? Or do you need to know about multiple paths possible to a solution?
Well, you need to know a little bit about your problem. There are actually sort of flow charts that I've seen. I think even scikit-learn has this flow chart. It will ask you, like, first you need to decide what kind of problem it is. Is it a let's say that you're talking about supervised learning. So is it classification or regression? Basically, do you have several classes that you want to find which class which category the output belongs to, or do you actually want to find the value? So that will be the first clue. Then maybe you look at how many features you have, what kind of data you have, how many pieces of, like how many, if you had this table like what we saw here with the iris data, how many rows you have, and then how many columns you have, how many outputs you might have if it's a classification, and that gives you an idea about the complexity. And if you don't have a lot of examples, if you don't have a lot of data, you don't want to choose a very complex model, because then the model will be so powerful, it will just memorize your data and will give you what we call overfitting. You don't want the model to be more complex than your data. So you basically you generally want to start with the simplest model you can that can actually do the job. If you can teach the simple model, then the generalization of the model will be probably better than more complex models. So you can start with a simpler one and then make it more and more complex. But there are some models that are like very powerful, and they also build themselves up according to the complexity. So they will work well with many problems. So they're almost like a sure bet. So they are random forest, support vector machines, and some of the simpler feed-forward neural networks. Now, if you know that it's a complex problem and it's a video analysis, image analysis, etc., then these are more problems that you will want to solve with deep learning. But you will need a lot of data. You will need powerful computers, and maybe in many cases you will find that there is already a network or a model that somebody trained. Like you can go to DJL and look at their model zoo, and maybe you'll find something that's pretty close to what you want. And then you just figure out what you can add to it, perhaps, because it's missing something that's specific to you. Like, let's say that this scribble thing that we did can detect a lot of objects, but you're also interested in something that it doesn't have. Let's say that you want to detect glasses. So maybe you have to go take that and train it more on glasses, and then maybe you'll change it so it will just tell you, are these glasses or they're not glasses, what I see here. And you have ones that also will take a picture and will tell you the glasses are here. They will draw like a frame around it. That's an object detection. So you need to be familiar with what's available is important, because you don't want to basically reinvent the wheel when it comes to it.
Yeah. My question to you is, what got you interested in machine learning?
I think that many years ago, these things were not very abundant. You didn't. When I was in grad school, and I was looking for interesting stuff, basically, sort of what was unconventional at the time. So one thing that attracted me just was neural networks by itself, because it looked like fascinating that you try to imitate the human brain, or in general, the biological nervous system. I also was fascinated at the time with the fuzzy logic, which we did not mention today, but fuzzy logic is also, to me, a very interesting subject, which is used a lot today in a control system, not necessarily in AI, but it can be. And fuzzy logic is when the logic is not just binary logic. Instead of 0 and 1, you can have values between 0 and 1, and it makes it very powerful. And when I went to look for an instructor, a professor at the university that will be willing to be my advisor for my thesis, I had a lot of people not wanting to deal with it. They said this will like make us outcasts. We don't want to start like sort of neural networks at the time were sort of became more commonplace, but before that, people who dealt with neural networks were like considered weirdos. And then when I brought up fuzzy logic, a lot of them were very turned off by that. And there was even one who told me, I don't want to touch fuzzy logic, and I also don't want to touch genetic algorithms. And the minute she said that, it sounded really interesting to me. What is genetic algorithms? It basically made me very curious. I never heard of it before. So I went, and that was pre-web. So I couldn't go on the web and Google it. I had to go to the library and start looking for publications about genetic algorithms. And actually there was a very good book that came out in 1984 that actually made genetic algorithms sort of more popular and accessible. And I'm talking about the 90s, but that book has been around for a while. Genetic algorithms started in the 70s, but there was a very complex book that a guy called Holland wrote, and most people did not understand it until in the 80s, somebody by the name of Goldberg wrote his book and made it a lot more accessible. So I had a lot of good material, and I really just was fascinated. Again, this is sort of an imitation of what happens in nature. Actually, I have another presentation that I do sometimes that's called bio-inspired algorithms, where I talk about genetic algorithms, and also there is something called genetic programming that is an offshoot of that, but also about other biologically inspired algorithms like ant colony optimization, which looks at how ants find food and how they communicate where the best food is and the closest, nearest source of food to other ants without talking. And there are also swarm algorithms where you use something like a swarm of birds or fish, where they sort of, each one is an individual, but they sort of conform to some general knowledge that all of them have, and you can use that to find the best solutions. There is something I haven't spoken much about. All these things, by the way, are mentioned in short in the last chapter of the book that I wrote, but so there are some examples there, but you can find them on, you can Google them, you can find a lot of information. One thing that's fascinating, and I haven't done much with, is artificial immune systems, where sort of recently people are trying to use that to detect viruses that you haven't, rather than knowing what a virus is and try to just add it to the list of viruses, try to create systems that will be able to detect the virus because it's so different from everything else that you saw, sort of like the biological immune system works. So these are, all of these are very fascinating to me, ways to try to deal with problems in ways that are not what we normally would think by writing a regular program that has all kind of, it's a logic that tries to imitate how we would go about it logically. So eventually these things all became part of AI. But AI, since the 90s till now, AI went through a period of a winter. It was called the second winter. There was also before that. So really only in the last maybe 6 years or so, it started to come back and became more known to people, and people started getting more drawn into it, and it became a commodity. And I think nowadays, as a developer, you really need to know those things, and you need to experiment with them for the very least. Because soon enough, I think any application will have some aspects of it. True that in many cases, as developers, we will just probably have to embed maybe prepared things into it, but I think it helps a lot to understand how it works and to also do some things with it ourselves. And also it opens a whole, basically a field for us to innovate and to try to think of new applications that were not yet thought of. So I highly recommend to try to learn more about it and to experiment with it and to also talk about it, because when you experiment with anything and you can go and make a presentation, then you really get to understand it and to know it, and you get to interact with other people that are interested. So I hope this was
another question if you have time.
Yeah, let's
one of the
more.
things, you know, being a Java guy, I like structure. And one of the things that irked me about the whole Python ecosystem is how to do versioning specifically of models and of parameters. So of the code, I mean, that's been solved by Git, and you know, everybody uses that.
Yeah.
But then I have a 4 megabyte or 20 megabyte model that Git won't grok, and then, you know, we just put it on an S3 bucket somewhere, and fingers crossed. So how do you do versioning of the metadata that comes out of a model while you're training it, etc.?
I think, by the way, this is what Attribio is trying to introduce with the provenance that I mentioned. It contains the information inside of it, so you can track it back and see where it comes from and how you trained it and what you did to create it.
Right, so you can reconstruct the path you took to get to a certain model.
Right. But I don't think there is an official way. I think you basically have to come up with your own way, and here you can use that to basically, if you take this metadata and you have it, you extract it and you save it, and you perhaps put that into source control. That would be possibly one way to go about it. Because review is new, I have not really experimented with that too much, so I don't have a great answer exactly how to go about it, but it's definitely something I would look into, and I can come back, and perhaps if you want to keep in touch with me, I can come back and possibly have a better answer.
Sure. So this is an opportunity for somebody to invent Git for massive files.
Possibly, it might be that somebody thought of it already and did it, but it's not necessarily going to be as good or the same. And the fact that I haven't seen it, maybe there isn't anything that became prominent yet.
Thank you.
Thank you, Eyal. This was really an amazing session. I'm very inspired to spend some time on the AI side of things, especially now that I can see there's a lot in the Java world, a lot of frameworks and tools to make it easier. I think we're a bit over time. So unless somebody still has an urgent question that if you can't ask it, you won't be able to sleep, I want to maybe suggest that we say cheers and thank you. But let me first see, is anybody that still have an urgent question for Eyal?
And you're always welcome to contact me afterwards.
Cool.
My name is also, if you just search my name, you'll find me on LinkedIn or Twitter, etc. So thank you very much for hosting me here. I had a blast.
Thank you, and thanks for making time and joining this event and doing the talk. I'm hoping we have you back soon on genetic algorithms. That sounds very interesting. And we will follow up with a recording link. I'm going to send it to our Jack, and then I'll send it, Eyal, I'll send it to you as well, so you can spread it to the other user groups who are also here. And yeah, thanks again. It's been awesome having all of you from all over the world.
Thank you, everybody.